All right, let's talk about one of the smartest and simplest tricks in all of modern AI. It's called Dropout. And believe it or not, the whole story is about how stopping little conspiracies from forming inside a computer's brain made it way, way smarter.
Yeah, I know it sounds kind of weird, doesn't it? A conspiracy inside an AI? But this question, it gets right to the heart of why Dropout is so brilliant. See, it turns out that to build a really tough, reliable AI, you have to stop its different parts from getting too cozy and dependent on each other.
Okay, so let's get into it. Before we can really appreciate the genius of the solution, we've got to understand the problem. And that problem is called overfitting. Trust me, it's a huge headache for anyone working in machine learning. So real quick, what's a neural network? Think of it like a powerful, brain-inspired machine that's amazing at finding patterns. It's got all these layers of connected neurons, and it learns by chewing through mountains of data. But, and this is a big but, all that power comes with a pretty serious downside. And here's that risk. The network can get lazy. Instead of actually learning the underlying rules from the data, it just starts memorizing the examples. It's like a student who crams for a test by memorizing the answers on the practice sheet. Sure, they'll ace that practice test, but give them a new test with slightly different questions, they'll totally bomb it. They didn't really learn the material. So why does this happen? Well, this is where the whole conspiracy thing comes in. Inside the network, individual neurons start forming these secret little packs. They're called co-adaptations. Imagine a team where one person is sloppy, but their partner is really good at fixing their specific mistakes. It seems to work, but it's incredibly fragile. If you take away the partner, the whole system just falls apart. So the big question for researchers was, how do you break up these little conspiracies? How do you stop the neurons from getting so codependent? And the answer, the big idea, came from a totally unexpected place: biology, specifically evolution and sex. This right here, this is the light bulb moment. In nature, sexual reproduction is constantly mixing and matching genes. This shuffling breaks up sets of genes that might work well together, but are ultimately fragile. It forces each individual gene to become strong and useful on its own, not just as part of one specific team. So the researchers thought, wait a minute, could we do that for our neurons? And that's exactly what they did. The solution is just so simple and elegant. While the network is training, you just randomly turn some of the neurons off for a bit. You drop them out. By doing this, no single neuron can ever be sure which of its buddies will be there to help. It can't rely on anyone else, so it's forced to stand on its own 2 feet and actually learn something useful all by itself. Okay, so how does this look in practice? It's a really clever 2-step process, and it works differently depending on if the network is learning or if it's actually being put to the test. So take a look here. On the left, that's your typical neural network. Everything's connected, right? But on the right, that's what it looks like during a single training step with Dropout. Some of those neurons are just gone, temporarily dropped out. It's a thinner, smaller version of the network. And here's the key. On the very next piece of data it sees, a totally different random set of neurons will disappear. It's constantly changing. So you've got step 1. During training, you're basically training a whole bunch of these unique, smaller, thinned-out networks, one after another in rapid succession. Then comes step 2, when you actually test the AI. And this is the truly genius move. You don't drop anything out. You use the entire, full-strength network, but you make one tiny change. You just scale down all the connection weights. And that one simple act is a mathematical shortcut that gives you the average wisdom of all those thousands of smaller networks you trained. It's incredible. Just think about how powerful that is for a second. With a decent-sized network, there are an astronomical number of possible thinned networks you could create. It's like training a massive army of slightly different AIs. But with Dropout, you get the combined benefit of all of them, basically for the price of training just one. It's just unbelievably efficient. Okay, the theory is beautiful, right? It's so clever. But the big question is, did it actually work in the real world? Well, let's take a look at the results, because they weren't just good, they completely changed the game. This number, right here, this is the one that really shook things up. Back in 2012, at the huge ImageNet competition, the winning AI, which used Dropout, got a top 5 error rate of just 16%. You know what second place got? 26%. That is not a small improvement. That is a massive, massive leap. It was a total revolution. And you can see what that looks like here. The network nails the cheetah, right? But look at its other guesses. Leopard, snow leopard. These are all really smart, reasonable alternatives. This shows it's not just memorizing pictures. It has a genuine, more flexible understanding of what a big cat looks like. And that's exactly what happens when you stop that fragile memorization we were talking about. And this success wasn't a one-off. It happened everywhere. Take the classic test of recognizing handwritten numbers. A standard network had about a 1.6% error rate. Not bad, but once you add Dropout to the mix and a few other tricks, that error gets cut in half, all the way down to a new record of just 0.79%. It's the exact same story on another really hard image dataset, CFAR 100. A standard AI, it had an error rate of over 43%. Ouch. But add Dropout, bam, that drops by more than 6 percentage points, down to 37%. Again, that's just a huge jump in performance from one simple idea. And what's so cool is that this wasn't just some trick for understanding pictures. This is the really important part. Dropout turned out to be this amazing general-purpose tool. It started setting new records in totally different fields, recognizing speech, classifying documents, even in things like computational biology. It just worked everywhere. So we know it works. The numbers don't lie. But can we actually see what it's doing inside the network's brain? The answer is yes. And honestly, the visual proof is maybe the most convincing part of this whole story. I mean, just look at this comparison. It's night and day. On the left, you see the kinds of features a normal network learns. They're messy, they're fuzzy, kind of noisy, and they overlap a lot. But then look at the right. That's with Dropout. The network learns these beautiful, crisp, clean features. You can clearly see things like edge detectors and curve detectors. They make intuitive sense. And that's the whole aha moment right there. By forcing those little conspiracies to break up, you make every single neuron learn to be a strong, independent worker. It can't be lazy and just assume its neighbor is going to fix its mistakes. It has to learn how to do its one job and do it really, really well. And get this, there was this totally unexpected, awesome side effect. The whole process makes the network way more efficient. Its internal activity becomes what we call sparse. That just means for any given task, only the very few most important neurons light up, the rest stay quiet. So the network isn't just more accurate, it's also more efficient. It learns to be powerful without wasting energy. And that really brings us back to where we started. The whole idea for Dropout was inspired by a simple, powerful process from nature. It really makes you think, right? What other brilliant, elegant solutions has nature perfected over millions of years that are just sitting there, waiting for us to discover them and use them to build the next generation of technology?